Recording is rolling. Welcome to Tuesday, January 20th. You know what? Actually, what I'm going to do is make one all video for here's AP, the agenda, here's honors. I was going to do different post lab activities today, but we're only going to have a couple minutes, so I'll just do like the same demos. So if you're in my honors class, here's what's due tomorrow. If you are in AP, here's what's due tomorrow, and of course, you guys got a quiz due Monday. You guys have unique quizzes per class, but we're all doing I want to okay, so our main topic today is going to be this oscillating spring lab. You guys all have this paper. Does anybody not have this half page on their desk? Okay. But we're going to save that for a little bit later in class today, because before I get to that oscillating spring lab, I want to tell you guys about musical scales and temperament. So because I know I've been telling you guys about waves, harmonic motion. We've been doing some stuff on sound and decibels. I never even told you guys about scales. So let's get this one. How many guys play musical instruments? How many guys? Ooh, bunch of guys. You guys play instruments. So on a Western scale, how many unique individual named notes are there before you cycle back to the next octave? Okay, usually 7 or 8 per scale.
8 in the scale, but 7 unique.
Yeah,
Right. And then if you also include all the accidentals, that brings you up to how many?
A lot.
12. Yeah, 12.
A lot.
So, yeah, a lot. You're not wrong. So, let me play on. First of all, here's a major scale. You're going to hear 7 unique notes and then the octave, so 8 altogether. Here's a C scale. Just a major scale. Then if I go add all the accidentals, count them all together. So I'll start with the root, I'll play them all up to the octave. So you should hear 13, right? 12 plus the octave. Right, so C. Yeah. So good. Now, why is it 12 notes? Well, that's what I'm going to be getting into and talk about these different tuning standards. So actually 12, actually it's been a really good way to divvy the notes. You'll see when I dig into the math, actually follows a logarithmic scale. You'll see that too, kind of like decibels. 12 is not necessarily like baked into any like hard physics though. So 12 notes in a scale is pretty universally used around the world. But historically, there have been like pentatonic scales, which kind of land on some of the same notes. So that's kind of thing. A lot of Middle Eastern music, like even modern Middle Eastern music, actually has 24 notes. So it has all the notes on the piano and plus some quarter tones between. So they get to 24. You can even create scales that have, I think it's like 19 notes or 31 notes, which it actually works out. You can hit some particular harmonic ratios pretty exactly, but those are like really weird scales to work with, although they are out there and there have been songs composed on them, but it's not really main standard. But so what's this deal with temperament and what does this have to do with the physics? What are the equations that are involved with finding the ratios of frequencies between notes in a scale? I'm going to start with equal temperament. So pretty much all modern instruments, including this digital piano that I'm using to demo up here, is equally tempered. And what that means is that the ratio of frequencies from one note to the next is the same everywhere. It's equal. So I'll start with, but actually this has only been a main standard for about 100 years. Before that, some of these other temperaments were used. So I'll start with this one, explain this one, and then I'll go back into the past and say what some of these other ones were for a long time. So equal temperament goes like equal temperament. The formula goes, if you're interested in what is the frequency of a particular note, say relative to some root note. So I'll start with the frequency of a root note. For example, one of the A notes is defined as 440 hertz. That's an A note, I think it's 440. And then multiply by, so multiply, I've got 2 to the power of n over 12. Okay, where n represents the number of semitones from the root note. Semitone is like a half step, right? So if you go from here to here, that's one note away, that's one half step, that's one semitone. Okay? And start to navigate this, make sense of this. So what if n was equal to 0? Because what is 2 to the power of 0? 1. It is 1. Yeah. So 2 to the power. Whenever I see formula like this, I start plugging stuff, playing around with it, and go, does this match with stuff I already know? And then what else, whatever insight can I get from it? Yeah, 1. So that means if you have a root note, for example, 440 hertz, I think it's that one right there, then multiply by 1. Okay, well, that just would be itself because you would be 0 steps away from itself. What if you go all the way to 12? Hey, 12 half steps, isn't that like a full octave? Right? And 12 over 12, that's 1. 2 to the power of 1, that's 2. Oh, so to go from here up an octave to here, you guys hear it's the same note, it's just 1 octave up. Okay. In terms of the physics, that's what multiple of the frequency? Double, yeah, that's double the frequency. Okay, so every time you go up an octave, doubling the frequency. Or it could go half. Like half. I just played a bunch of A notes. Those were all A notes that you guys heard. Just okay, what about some of the other parts? Oh, I should write this down. So root is like 2 to the 0 over 12, which is just 1. So it's 1 times itself. Okay. The octave is like 2 to the 12 over 12, which is a factor of 2. So it's like double the frequency. Okay. What if, do 2 other examples here. Let's look at the perfect fifth. Let's look at the fifth. And later on, I'm going to do the major third as examples. Okay. So the fifth, let me play that interval. Let me go back to just a C note. Oh, so the root is C now. Okay, here's what the fifth interval sounds like. Because here's the G note, which is the fifth. That sounds pretty good, right? So that harmonizes really well. Okay. Now, if you count the number of semitones, let's count them. You guys count 7? Okay. So 2 to the power of 7 over 12. Okay. The fact that we're dealing with powers, you guys know this is going to follow a logarithmic scale, right? Logarithmic scale. You guys have seen some log scales in the past couple weeks. What is 2 to the power of 7 on 12? It is 1.498. Huh. Interesting. Because that is very, very, very close to what? 1.5. In fact, you know what? If it were harmonizing exactly, then it would be a 3:2 ratio. That is actually the ideal ratio. Now, can your ears distinguish between the true harmony and the equal tempered? I don't think mine could. Maybe somebody in this world, there's billions of people, but it's extremely close. Right? What about say major third? Okay, so here, play guys. Here's major chord. Here's the interval. Or here's 1 octave down. So there's a major third interval. Okay, let's count the notes. You guys count 4? Okay, so it's 4 notes up. So that's 4 over 12. Okay. What is 2 to the power of 4 over 12? That is, 1.2599. So 1.2599. Okay, something like that. Maybe we should get an extra digit on that for consistency. Okay. That's really close to what ratio? 1.25 is pretty close to 5/4. It's like a 5:4 ratio. Okay. In fact, if it had been a perfect harmonization, it would have been a 5:4 ratio. Okay, so this doesn't line as closely as the 3:2 did, as the perfect fifth, but it actually does line pretty close. Right? So actually, this harmony, this major third harmony, is not quite as clean as the fifth is. It's a little bit muddier because of this equal tempered, right? It's just the standard for tuning the same. Okay. Pay real close attention. You might even be able to hear a slight beat frequency to it. So it's a little bit wonky. All right. So again, equal tempered modern standard follows this log formula, and it hits certain harmonic ratios that actually land pretty close to their ideal harmonic ratios. Okay. Oh, okay. Well, what were we doing before equal temperament, or what are some different perspectives on how you could say tune an instrument? Okay. So hit these real fast. I give my best explanation of these, which is pretty much my reading of Wikipedia last night. Let's just go with that. So just intonation, what I got from this was if you have perfect harmonic ratios for one particular key, and it's usually the key of C. So you pick the key of C, and then the fifth from that, the G key would be exactly a 3:2 ratio, and the E key would be exactly a 5:4 ratio. Then as long as you're playing in the key of C, then you get like really nice sounding music, like really clean, like perfect harmonies. The downside of this, because each of these temperaments has a trade-off, right? So the downside is as soon as you switch keys, then your song sounds different. Okay? And it's a bit wonkier, the harmonies don't line up exactly, right? Versus remember equal temperament, which is what the world is pretty much settled on. You could write a song and you could switch it to any key, and yeah, it'll sound shifted up or shifted down, but besides that, it doesn't really have a tonal difference, right? But just in an intonation, actually, that would be also true for these other two, right? If you switch keys, they sound a little bit different, right? Pythagorean tuning, the emphasis, the priority is on this perfect fifth ratio, so 3:2 ratio. So you start from a root note, you expand out from there and make the perfect fifth, like exactly 3:2 ratio. But then, of course, there's a trade-off because the other notes don't exactly line very well with their harmonic ratio. So I want to say like the major third is particularly wonky, and that leads to the next one, mean tone temperament. Mean tone temperament is kind of a compromise between Pythagorean tuning and equal temperament. So it's an adjustment of Pythagorean tuning so that the major third is not like terribly far off. Okay? But there's an interesting consequence of these temperaments that were used before equal temperament. Like if you go back to 1800, let's say 200 years ago, equal temperament was not really favored. So say if you're watching like Bach play on a piano or something, he was probably playing on one of these other ones, maybe just intonation or something. That's how they tuned pianos back then. Okay. And if that's true, we switch my screen over. Then each key actually had its own sort of character to it, okay, which is not true for equal tempered. Equal tempered, everything's just like the same. Okay. So you get things like this. So let's say you adjusted everything for C. Well, C would be like pure, all the harmonies would be perfect. But then that would have interesting consequences for these other keys. Let's say you wanted to write a song that involved, hey, how about this, like feeling of anxiety, right? You might go to the composer and say, I want something that feels anxiety. They say, oh, well, you want a deep, sharp, minor chord, right? Or hey, maybe something rustic. I don't know, like G major, gloomy key. We have a triumph over difficulty. And so each of these would have its own character attached to it. Again, this page you guys are seeing right now has nothing to do with the modern digital piano. This piano right here has nothing to do with the screen that you guys are seeing. But if you go back 200 years ago, yeah, that would have been the case. All right, so enough of music stuff. Oh, let me break out the slinky. Nice long slinky here. Right, now, if you're watching this video, I'm going to do some stuff off screen, but I'll try to keep this kind of short. Here's what I'm doing with the slinky. I'm going to pulse a longitudinal wave. So longitudinal. Okay. I'm going to do a transverse wave, and then I'll hang this vertically and drop this thing, and we're looking for interesting things. So if you're watching the video, hang tight. I'll be right back. Put this to the store, stretch this, and send some pulses. Do you guys see a pulse going back and forth? Okay. Now, this is like a longitudinal wave. Is this a standing wave? No, it'd be really hard to do a standing wave. A standing wave would be like, there'd be a pulse that would like it was just like hovering in one spot. Okay. Maybe you could do that. I don't know if I could do that. Okay. But I see a pulse like racing back and forth. I wonder what speed it's racing back and forth. This is something I think we covered yesterday. You guys remember speed of a wave on a string is like square root of the tension divided by linear mass density? Well, this is probably a really kind of small tension. It's a slinky, but also a very large linear mass density. It's made out of metal. So if you have a small tension divided by a large linear mass density, take square root of that, that would be probably a pretty slow speed, wouldn't it? In fact, it's slow enough you can actually watch that pulse going back and forth. Let's do a transverse wave. Hey, it's a standing wave. Not anymore. Oh my. My one Slinky. How does this happen? Okay. Really? Really? We are having some Slinky difficulties. Yeah. I don't want to waste your class time. I'm trying to get this untangled. Hang on. I know the solution. Oh, really? Really? Still? Yeah. Okay, I'll get fixed up here. I'll get fixed up. All right, we're back. We're back. Yeah. Did I ever play you guys a Veritasium video where? Okay. Yeah. Great. Okay. All right. Where we hold the Slinky vertically and just drop it. You guys see this? Did I show this to you guys one day? All right, so I'm gonna steal this from a Veritasium video. Go to YouTube, Veritasium, type in Slinky drop. You can see this. Now, when I drop this, here's what you're looking for. Is the bottom of Slinky right now, free body diagram. There's a so like this piece right here. There's a weight pulling down, there's a tension pulling up, and it's in equilibrium, right? So if I drop this, what's gonna happen to the bottom?
Just stay still.
Yeah. Do you guys see that? There's like a
I
time delay.
think you did show us that.
Okay, yeah. Okay, so you guys remember this? Right, so one perspective on that is that there's a time delay. It takes some time for that information to go down the Slinky. In fact, it's probably like the speed of sound. Wouldn't that be the limiting speed, like speed of sound? Right, to propagate through some material, right, which is pretty slow there. Right. All right, so back to here. I have a tiny Slinky, and you guys got the slide paper out? Right, so the slide page is going to be in two halves, got the front half and the back half. Okay. And okay, so you guys see the setup. It's going to be vertical. This thing's going to oscillate up and down. And on this side, we're looking for what is, so if let's say this is unstretched and I just drop it, it's going to stretch to some X max. And then it's going to oscillate back and forth, and eventually reach X equilibrium. Now, the other day, I derived or helped you guys walk through to figure out what is X max compared to X equilibrium. And what's the textbook answer to that? What's this ratio?
2 to 1.
Should be 2 to 1. Right? Guys remember that? So we're going to see experimentally if that's the case. And then in the equilibrium position, I bet there's an mg down and a kx up. Right? Do you think we could figure out what the spring constant is using that? Right. Then later on today, we're going to look at this setup. Time period of a pendulum is equal to 2 pi times the square root of m over k. Now, what we did about a week ago, pendulum swinging back and forth, the time period was 2 pi times the square root of L over G. And the way we approached that particular lab was sort of derive that formula from scratch. But this one, let's say we know that, and we'll let this oscillate up and down. So it's going to what's the time period of that oscillation? And we're going to check this textbook formula and see how close that is. So it's just saying. Oh, and when we get to that part, somebody's going to have to time this. So somebody has a stopwatch function on their phone. And so yeah, you must know. Right, so first one, let me pick some different masses. I'm going to go with the 50 grams, so let's call it 0.050 kilograms. I'll have 100 grams, so that'd be 0.100 kilograms, and 200 grams, 0.200 kilograms. Okay, guys got this? Those are, anything smaller doesn't really work, and anything bigger doesn't really work either, so we'll just go with those three. Okay, okay, let's try this over here. Gonna move my camera so that guys online can see what's going on here. Right, make sure that, okay, meter sticks in camera. I think right up there. Okay. So X max, so I've got the 50 gram mass, 0.5 kilograms. I wonder how, okay, so right now it's unstretched and the bottom of the mass is aligned with the 0 centimeter mark. And so let's see, how far is this going to drop down? I got about this far. It looks like 26 centimeters, I think. I might be off by about a centimeter, but let's go with X max was 26 centimeters. Okay. Now, if that's true, what do you guys think the equilibrium position is going to be pretty close to? Maybe half of that, about 13 centimeters. Let's see if that's true. See how close that is. All right, so unstretch, align to 0. Then slowly lower this down. Let it go. That is at it's reading about 15. About 15. That is pretty close to half. About 15 centimeters. And what's the scale reading at that equilibrium point? Okay, so let's take this. Okay. And what should the weight of this 50-gram mass be? About 0.5 newtons, right? 0.5 newtons. Okay. Let me see what the empty scale is, because this is an issue I've been thinking about. Usually, any textbook probably have with a spring scale, it'll say the spring has negligible mass or weighs nothing, some version of that. Okay. But I'm getting about 0.2 newtons. So when I hang on this 0.5 Newton mass, I mean, that is pretty significant ratio, right? I'm getting 0.7 newtons, right? So the scale's rating 0.7 newtons. There's actually 0.5 newtons of force, you guys know. So there's some weight. So there's a little bit of variation along the spring. But just to be consistent with this lab page, let's go ahead and use 0.7 newtons. But you guys know that that's a little bit variable, but especially for the smaller masses, it's going to be proportionally kind of variable along the length of the spring. Right. Last column says spring constant newtons per meter. Hey, Hooke's law, F equals kx. So if you take this force and divide by this equilibrium length, shouldn't you get the spring constant? Right. Let's try that out. So what is 0.7 newtons divided by 15 centimeters? I'm looking at 0.047 newtons per centimeter. Okay. So guys, what to is I just made up this paper a few days ago, just staring at the screen, so I didn't know how the numbers were going to turn out. Let's convert that to newtons per meter for two reasons. One is that it's a nicer number. The other is that that's usually how you see a spring anyway, right? How many newtons per meter would that be?
4.7.
4.7. Yeah. So make your own column off to the right, K in newtons per meter, and that would be 4.7. Okay, so got a spring everything. Let's try this with some of the heavier masses. Now, the heavier masses, I'm thinking, are going to be more accurate because the ratio of the spring scale mass compared to the hanging mass gets closer to 0, which gets closer to an ideal textbook situation of like a negligible mass spring. Okay. Let's try this again. Okay, so start this at 0, okay, and woo, okay, look like 60 something. Let me see exactly. I think I was about here. I think it was about 70 centimeters, I want to say. Yeah, might be missing out by centimeter or so, but let's go with 70. Okay, 70 centimeters of X max, 70. Right. Equilibrium position. So I'm going to guess around 35 centimeters, but we're about to find out. Okay, so figure it out right there. Hang down. Turn the. Okay, looks like 32. I'm going to say 32. That's pretty close to half. Okay. Okay. Then, force reading. Okay. So keeping in mind that the spring itself has a little bit of weight, it's going to throw us off a little bit, but I'm looking at 1.2 newtons. Oh, of course it should have been that, because 1 newton plus 0.2 newtons. Right? So 1.2 newtons. So, okay, and then for K, if you take this 1.2 newtons and divide by X equilibrium of 32 centimeters, so it's 1.2 on 32, I'm looking at 0.0375. Okay. And wouldn't you call that like 3.75 Newton per meter? Okay. Okay. Yeah, okay, spring constant. Okay, let's do one more mass. Let's do 200 grams. 200 grams.
Oh boy. So it's gonna be a fun one. Actually, I think it's gonna go beneath the meter stick, so we have to estimate a bit. A little fuzzy science. Alright, try it again. Get another good look. I'm gonna try to catch a position. Want to say like down here?
Yeah.
Okay. How about 25 centimeters below? Call it 1.25 meters. Yikes. Right. So 125 centimeters about. That's exactly accurate, but we'll run with it. Let's see, where's the equilibrium going to be? Get kind of a tight fit today for all the stuff I want to get in. So, normally you'd be, if you're really scientific, you'd be a bit more meticulous than I'm being right now. Maybe that's a lesson too. All right, so this hangs out at, that is at 69 centimeters.
Nice.
What today? And, oh, what's the force reading on this? Force reading is 2.2 newtons. It's reading 2.2 newtons. Well, that's oscillating, but before it was oscillating, it was like 2.2. Oh, of course it should have been 2.2 because 2 newtons from the weight and then 0.2 newtons from the spring. Okay. All right. Turn the camera back. All right, so back to this page. Let's figure out K, newtons per centimeter. So 2.2 newtons divided by 69 centimeters is 0.0319 newtons per centimeter, which is like 3.19 newtons per meter. Okay. Of course, it's the same spring over and over, so it's good that get spring constants kind of in the ballpark. Okay, so it looks like spring constant is probably about, again, if it's more accurate for the larger masses, I would say probably somewhere 3.5 Newton per meter. That's what I'm thinking, probably somewhere there. That should be what the spring constant is. I've got a couple of graph spaces up here, so let's get some graph practice. This graph says X equilibrium versus X max. So we're taking these two columns and doing X, Y values, treating this like X, Y coordinates. So it looks like my X value goes up to 125, Y value goes up to 69. So let's scale those accordingly. Those centimeters are already labeled. So it's kind of like, so 0, 25, 50, 75, 100, 125. And for the Y values, let's go, maybe same scaling. 0, 25, 50, 75 centimeters. Okay. Let's plot these points. So we got 26 over 15 up, 26, 15, that's right about there. We got 70 over 32 up, it's right about there. And 125 over 69 up, that's right about somewhere there. Okay. Oh, okay, look at those points. They line up on a straight line. And I wonder if you guys are going to get this. Somebody, what is the slope of this line approximately? Or the ideal textbook value, either one? That's a what to what ratio? Yeah. And then the reciprocal of that did like a 1 to 2. Right? If I flipped the axes, it would have been 2 to 1. That way it's 1 to 2. Yeah. Like that. You guys got it. What about this graph? F versus X equilibrium. Well, X equilibrium, naval scale is 25, 50, 75. 0, 25, 50, 75. I mean, what was the y-axis on the other graphs, not the x-axis here. Okay. Let me subdivide this. So 5 centimeters each. Then the force values went up to 2.2, so maybe like 1, 2, 3. So 0, 1, 2, 3 newtons. Plot these points. So we got 15 centimeters and 0.7, that's right about there. We got 32, 25, 32, 1.2 is right about there. and 69, 2.2. It's right about there. Hey, no, that was pretty well lined up in a straight line too. Maybe not exactly, but kind of close. Ideally, it should be a straight line, because what should the slope of this line represent? K, it is. This graph is Hooke's law, F equals KX. Yeah, that could be an AP question. I have to say, figure out K graphically. You say, Hooke's law, F equals KX. Well, K should be the slope of F versus X. Guess that? Guys good? All right, guys ready for oscillations? Just got the graphs. I was gonna tell you guys, I'm gonna pick this up at the end of class. So if I'm going like way too fast or something, then if you need to copy this down at home and bring it in tomorrow, you can. But if you keep it up, then pick this up at the end of class and give you guys points for this. Guys good? So oscillations. Now, this one, start by knowing what the textbook formula is. T equals 2 pi. So this T is time period, right? So time period. Right? Other contexts might be tension or temperature. Right? Here's time period. Right? 2 pi times the square root of m over k. Let's use the same three masses as before. So that's going to be. Wait, hold on. Here's my two. Okay. So we got 0.050 kilograms, 0.100 kilograms, 0.200 kilograms. That's this guy, and this guy. So we're gonna count what's the time to do 10 oscillations. So that 1, 2, 3, 4, right, down and up is one full cycle. Right. Then we'll divide by 10 to get the time for one cycle. Right. So you ready to read?
Okay.
Right, so switch camera over.
There's no choice.
Get that. Oh, thought you pre-volunteered for this.
I volunteered for it.
Oh, okay. You just got volunteered. Yeah. We'll go that way. Right, so ready? Actually, I'm gonna do this. I'm gonna let this hang to equilibrium and say I pull it down like 3 centimeters. Shouldn't it bob up and down? Like up 6, down 6. Okay. Right, so ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How much time?
7.96.
7.96. Okay, let's go ahead and grab all the data first, and we'll crunch it later. Okay, so 100 grams. Okay. Okay, so equilibrium right about there. Pull it down. Ready?
Yep.
And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
11.10.
11.10. And then 200 grams. Okay, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
15.65.
15.65. All right. Thank you. Now, really did that way, get all the data first because easier with the camera. But what I would like to have done here, let's figure out time for one full cycle would have been 0.796 seconds, something like that. Okay. Oh no, I'm covering these up because let's pretend we don't actually have these yet. Because I want you guys to predict what they would, pretend you don't know. Okay. Take a look at this formula. Okay. So if see going from 50 grams to 100 grams, you're effectively doubling the mass. Okay. All right, so this formula, if you do a factor of 2 on this mass, which is what we did from first, second row, factor of 2 on this mass, it's the same spring, it's the same spring constant. Then time period should increase by what factor? This 2 is inside the square root, right? Shouldn't be the square root of 2. Okay. So if the original time was 0.796 seconds, original time period. If I multiply by the square root of 2, it's about 1.414. That is, you guys see 1.13? It should be 1.13 seconds. Should be 1.13. Or whatever I'm covering divided by 10, which is 1.11. Look at that. Predicted 1.13, actual 1.11. How about this? If you go from the first row to the third row, you see it's a quadrupling of the mass, 50 grams to 200 grams, it's quadruple. If you do factor of 4 on that m for the same k, the time period should increase by a factor of what?
2.
2, because it'd be the square root of 4. I said. Okay, so what is 0.796 times 2? The square root of 4 is 2. Should be 1.59 seconds. Should be 1.59. What I'm covering divided by 10 is 1.565. Yeah, that's really close to 1.59. Okay, okay, so this that relationship looks like it's holding up. Okay. That's good. What is K? Okay, now here's where I knew you guys could do this. If you know M and you know time period, you could solve for K. Oh, you know what? This was one of those AP Classroom questions that you guys remember. If you have exactly the experiment we just did, it's like vertical spring, and you want to solve for spring constant, they said, how could you do that? And they gave you 4 measuring tools. What 2 measuring tools would you need? A what and a what?
Top button about.
Yeah, a timer to measure the time and a balance to measure the mass, right? And that was the answer. You guys remember that? So that's exactly what we're doing here. And then you can just algebraically rearrange this and solve for K. I did that for you guys ahead of time because I know you can do it. So it's 2 pi quantity squared times mass divided by time period squared. Let's try that out. What is 2 pi quantity squared times the mass in kilograms, 0.05 kilograms, divided by 0.796 squared. I'm looking at 3.12 newtons per meter. The next line, it's 0.10, and then the time period was 1.11, where that is. You guys get what I'm getting? 3.2. Hey, look, that's pretty much in line with the first one. And what about this one? It's 200 grams, that's 0.2 kilograms. The time period was 1.565. Square that. Looking at 3.22. All right, so it looks like the spring constant is, yeah, about 3.2, which is that's what we were getting before. And remember the way we did before on the first side with Hooke's law? I was saying the larger masses are probably giving more accurate data. Look, the very last one we got with the largest mass, 3.19. That is right in line with these right here. Okay, you guys see that? Guys good so far? Okay. Now, one more thing I want to do with this is this graph. Couple of reasons. One is I like graphs anyway, but another reason is I could totally see AP asking this as an FRQ and they want you to draw a graph and extract K from that. I mean, it's a common thing. You guys have seen this like so many times now. Where you're, okay, well, what graph would I have to set up that maybe there's some kind of linearization? How can I take this formula and linearize it so that what I'm solving for K represents like the slope of that line, right? So yeah, you guys have seen that question like in so many different contexts over the last few months. I'll walk you guys through the algebra, although what I'm about to do, hopefully you guys could do anyway, or maybe stay a step ahead of me. How can you linearize this to say put it in the form like y equals an x, sort of, okay? So that this K represents the slope. Okay? So I'm going to start by copying down this formula, give you guys a little head start. Okay. And I want this K to land being like the slope of something like y equals an x, sort of. Okay? So maybe I'll square both sides. T squared equals 2 pi quantity squared multiplied by m on k. Okay, so that step was nice because it got rid of the square root. So I just buried this from the square root. I'm going to cross multiply the k. Maybe I'll swap both sides while I'm at it. So 2 pi quantity squared m is equal to k times t squared. Okay. Actually, that could do it right there. If you graphed 2 pi quantity squared m on the vertical axis versus t squared on the x-axis, then that would linearize and k would represent the slope. Perfectly valid. Just for the graph I printed, I'm going to do one more thing. I'm gonna do it this way. Just take that 2 pi squared and divide that down. Okay. Not because you have to, but because I pre-printed it like that. Okay. Hey, does this look like y equals slope times x? That's exactly what that looks like, isn't it? Right. Okay, so really good chance you're gonna get something kind of like that on the AP exam for an FRQ, and you see that? So this last column says t squared over 2 pi quantity squared. And now you guys see where that's coming from. That's because that's gonna be your x values. They're gonna have some weird manipulated axis. So let's fill in this column. This is kind of an abstract idea. It's in square seconds, but let's figure it out. So what's 0.796 seconds being squared divided by 2 pi quantity squared? I'm looking at 0.016 to be square seconds. The next row, 1.11 squared divided by 2 pi quantity squared. Looking at 0.031, and then 1.565 squared, and then 0.062. So now mass versus that. Oh, also, there's a typo. Some of you guys may have caught the typo. You see down this axis, scratch out this expression. That was supposed to say t squared divided by 2 pi quantity squared. I didn't actually catch that until I printed these all out though. You guys replace that. So we're graphing mass versus that square seconds quantity. So mass, we have to scale up to 200 grams. So let's go 100 grams, 200 grams, or in kilograms would be 0, 0.1, 100, 0.200. Okay. And then this weird abstract column goes up to 0.06. So let's go, say, 1, 2, 3, 4, 5, 6, maybe something like that. So 0, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06. It's a little bit right that still fit on the paper. So coordinates, got 0.016, it's about here, is 50 grams, is right about here. Gonna have 0.031 is 100 grams right there. And then 0.62 is at 200 grams right about there. Hey, those points line up in a straight line? Sure do. See if you guys are following. What is the slope of this line equal to? K. Yeah, which should be about 3.2 or so Newton per meter. You guys got that? Oh, actually, we're doing really good on time. So let's do this this way. As soon as you guys wrap that up, you've got all the graphs and everything. Go ahead and pass those forward. I'm going to spend the rest of the class doing some demos with you guys, some video demos, and then I'll just pick these up from the front rows.